Alright, so for problem 4.6, the first problem of homework 4, task is to use nodal analysis, also known as the node voltage method, to find VO in the circuit. Number one thing we're going to do, label our nodes. And let me do that actually in green. Oh, I missed one. There's that, and there's that. So if we set that to 0 volts at the bottom, that makes this 25. You can call this V1. This will just be as VO because it's already there. So, since we're only looking for VO, to simplify the analysis, we can combine these two resistors and not worry so much about V1. Just that way it'll be a straight shot to the 25 volts instead of the 25 volts minus V1, blah blah blah. Anyway, in nodal analysis, you consider each node that you're analyzing as all the currents are leaving that node. It may not be the case in which you'll have a flip sign in the final answer, but it's okay. Just assume all of them are leaving. So we'll do a KCL at VO and assume all of the currents are leaving. And we'll just use the equation for current in the resistor. So anyway, VO minus 25 divided by 120 plus 5, which is our equivalent series resistance right here. And then we're going to do V out minus 0 divided by 25 plus 40 milliamps, leaving that node, all equals 0. So next thing is we're going to simplify. We have one equation, one node, so it'll be pretty simple. Multiply everything in here by 125. Just get rid of the fractions. We're going to end up with VO equals, or minus 25 plus, let's see, 125 divided by 25 is 5, so 5 VO. This one I use the calculator for, 40 milliamps times 125 ohms is 5 volts. So now we're going to solve for VO. Put everything to the right side, so VO is going to be 20 divided by 6, which is 3.3 volts repeating. So this one's pretty simple. And using that information, you could actually find V1 really easily if you wanted to. But the problem only asks for VO, so we're going to stop here. 4.11, we're going to follow that same process of nodal analysis to solve this circuit. So first thing we're going to do is label our nodes. Okay, so I'm going to call this one ground, which will make this 144 volts, this V1, and this V2. Just reusing the circuit labels that are already in the problem. No reason to get rid of them. Then we got to consider each node, do a KCL there. So in nodal analysis, you assume all currents are leaving that node, and then do a KCL for that node. So we're going to do KCL at V1, and I'm going to go straight from the currents to the equations for the current in a resistor, just Ohm's law. So anyway, V1 minus 144 divided by 4 ohms plus V1 minus 0 over 10 plus V1 minus V2 over 80 equals 0. Going to do that same process for node V2. And I draw the currents for that one, that node in green. Alright, so I'm going to start out with V2 minus V1 over 80 plus V2 minus 0 over 5 minus 3 amps equals 0. And why minus? Well, it's because a little arrow here is in the opposite direction of the current flowing into it. Now, since we don't have an equation that models this component in terms of the voltage drop, we can't flip the sign basically like we can here. So we're just going to leave that as a current. So now that we have the equations, we have two equations, two unknowns, we have a linear system of equations to solve. Now, you can use whatever method you like to solve linear equations. You can use substitution, elimination, superposition, matrices, but I prefer to use my calculator for these because, quite frankly, it's tedious work, and if you set up the equations correctly, then it's going to be a lot faster. So I'm going to put I'm going to call this, let me put it in a color, call this equation 1 and this equation 2. And we're going to try and simplify those so it'll be easier to put into a calculator. So notice that V1, or equation 1, if we multiply it by 80, we'll get rid of that denominator. Hold on. Sorry about that. I'm just trying to make sure that I can reduce the echo in recordings. Alright, so I'm going to multiply equation 1, all those terms, by 80. We're going to end up with 80 divided by 4 is 20, so 20 V1 minus 144 times 20 plus 80 divided by 10 is 8 V1, and 80 divided by 80 is 1. V1 minus V2 equals 0. So if you simplify this, you're going to have, let's see, 144 times 2 is 288 times 10, so 2880. If I put it all into a set of like a system of equations, you're going to have 29 V1 minus V2 equals 2880. I'm going to do the same thing for KCl V2. So multiply everything by 80. V2 minus V1 plus...
Sorry, I didn't get that.
V2 minus V1. 80 divided by 5 is 16. V2. And then 3 times 20, so 240 equals 0. Simplify all that, you get negative V1 plus 17 V2 equals 240. So set up this system of equations basically. So I'm gonna put these into my calculator real quickly. It'll tell me right away what V1 and V2 is if I set up those equations correctly. But you can use whatever method of solving linear systems you prefer. I just happen to prefer using a calculator. Okay. So while I was talking, I was punching these in. I get V1 equals 100 volts and V2 equals 20 volts. So now we know everything we need for the rest of the circuit. If we wanted to solve for any of the currents or whatever, it'd be super easy because we already know the voltage drops. Alright, so let's move on to the next one. Alright, so for 4.14, we're going to follow up and continue using the nodal analysis to solve this circuit. So we have 6 currents to solve for in this circuit, and we can find all of them using Ohm's law, but we first need to know the voltage drops across the resistors. So first thing we're going to do, label our nodes. That's a node, that's a node, that's a node, that's a node, and that's a node. Alright, now we're going to figure out where we want to put our ground. Now it may be tempting to put the ground over here because there's more things connected to it. Well, not necessarily more, but there's a lot of things connected to it. There's also a lot of things connected over here. But putting the ground there doesn't necessarily make anything simpler. We want to reduce the number of unknowns we have in our system so we can reduce the number of equations we need. So if I were to say put the ground here, we have 5 unknowns. So which one are we going to pick? Well, if we put the ground reference right here, say this is 0 volts, that's going to make this 125 volts, and this minus 125 volts. Now that cuts down our unknowns to only 3. So I'm going to call this one V1, this one V2, and this one V3. And we're going to set up a system of equations from using nodal analysis. So for V1, I'm going to draw the arrows in black for the currents. And then I'll use blue and then green for the others. Alright, so KCL at V1, there is V1 minus 125 divided by 1 ohm plus V1 minus V2 divided by 6 ohms plus V1 minus V3 over 24 ohms equals 0. Do the same process for V2. I'm going to draw my arrows just so you can work along with me. Alright, so V2 minus V1 divided by 6 ohms plus V2 minus 0 divided by 2 ohms plus V2 minus V3 divided by 12 ohms, all equals 0. And finally, KCL at node V3. This one I'm going to do in green. So current going this way, current going this way, and current going this way. Once again, V3 minus V2 over 12 plus V3 minus 125, or minus 125, so plus negatives cancel over 1. And just V3, yeah, okay. Plus V3 minus V1 divided by 24 equals 0. Alright. So now we have these equations. We can put them into, we can solve them, substitution, elimination, blah, blah, blah. But I prefer to do the calculator analysis. So I'm going to basically set up a system of equations and then punch it into my calculator and have it do the heavy lifting for me. Alright. So 24 P1 minus I'm going to pause the video and I'll be right back with all this. Okay, so I set up the system of equations. Now if you're confused on how to do that, basically all I did is I took the greatest common denominator with all of them, multiplied them all by that, and ended up with these 3 equations. So this is like the KCL for V1, the KCL for V2, KCL for V3. Now, this is where a good example of where using a calculator can be very helpful. because the answers here are very hard to get by doing hand analysis. You can use linear algebra to do it, but a calculator will do it just as well. You can use the matrix function or the linear equation solver or whatever you want to solve these. Anyway, so the voltages I get here, V1 is 101.24 volts, V2 equals 10.65 volts, and V3 equals minus 106.57. Now I am rounding, so whenever we calculate the currents and everything, we may get a little bit of error from that, but we're going to make sure everything makes sense in the end. So anyway, now that we know the voltage drops, we can find each current in this circuit. So first thing I'm going to do is I1. So we know V1 is 101.24. So we're going to have I1 is 125 volts minus 101.24 volts divided by, I think it's 1 ohm. So see 125 minus 101.24, 23.76 amps. And we're going to follow this same process for each resistor. That's why we have V2 minus 0, so V2 divided by 2 is it's going to be 5.325, I think. 5.3, yeah. Let me just double check because sometimes I'm wrong. Yeah, I had it right. Amps, and then I3 is V3 minus 125, so plus 25. Let's see. 106.57 minus, so divided by 1, so we get 18.43 amps. And V1 minus V2 for I4. And I4 is 6. Okay. So 101.24 minus 10.65. Sorry, calculator. 90 divided by 6. End up getting 15. Let's just say 15.1 amps. I5. V2 minus V3 over 12. So V2 is 10.65 minus a negative number is a plus, so plus 106.57 divided by 12. I get about 9.768 amps. And for I6, I believe it's, yeah, V1 minus V3 divided by 24. Alright, so 101.24 plus 106.57 divided by 24 is 8.625, or 8.65 amps. Okay, so now we find out the branch currents. We're going to test that solution by ensuring that the power in is the same as the power out. So to do that, we're going to do our typical I squared R. So let's find power in 1. So 23.76 squared times 1 is 564-ish watts. So I'll just do 5.5 watts. Power 2, we're going to do I squared R again. 5.325 squared times 2 is 56.71. P3, I squared R, 18.43 times, what's the value of I3? I think I3 is a 1 ohm resistor. Yeah. So just square the current, end up with 339.67 watts. P4, 15.1 amps squared times 6 ohms is 1368.06 watts. Power 5 is going to be 9.768 squared times 12 ohms. 1144.9 watts. And power 6, 8.65 squared times 24. You get 1795.74 watts. Okay, so first thing I'm going to do is I'm going to add up all those results just to save a bit of time later. Add them all up. 564.5 plus 56.71 plus 339.67 plus 1368.06 plus 1144.9 plus 1795.74. Okay, I get about, I'm going to round it, say the total power dissipated is 5270 watts. So now we're going to compare that to the power supplied. So we got to find out how much current is flowing through these sources. Now, if it wasn't for the 2 ohm resistor in the middle, then we could find it by just finding I3 or I1, but there is a split there. Anyway, so we have I3 going in to the 125. So we'll say that PS1 is going to be I3 times 125, and the minus because we're supplying. So I3 is 18.43 times 125. We get 2303.75 watts. Say PS2 is going to be, I think it's I2 plus I1. I2 plus I1 times 125. Okay, so I2 is 5.325. I may have made a mistake, because this is going to be a big number. let's see, 23. Let me double check my math. I'll be right back. Yeah, I did make a mistake. I shouldn't include I2 because the common return path is, it's flowing towards the common return path, which is ground. So it's technically not supplying any power. Anyway, I1 times 125. So I1 is 23.76 times 125, 2970. So 2970 watts being supplied. So I say PS is PS1 plus PS2, 2970 plus 2303 is approximately the same as, it's 5273 watts. Now, there's a discrepancy here, but I did use a lot of rounding when I was calculating those currents before. And it's close enough to say that it's within the margin of me being a little bit, I don't want to say lazy, but expedient with the calculations. But you can see that if you include the extra decimals, it would all end up working out. So we have successfully solved this whole circuit. And this one is definitely, I think it's one of the harder ones that we've seen yet, simply because it's the math part. It's always the math part. If you get the analysis down in terms of how to set it up, everything, calculators, computers, they can all do it a lot faster than you can. Just focus on getting your physical intuition, everything like that down. That'll help you a lot more than mastering solving linear systems. For problem 4.17, task is to, let me actually get this pen working, is to find the power supplied by the dependent source right over here. Now this circuit is going to be the first time where we have to introduce a concept called supernode for nodal analysis. I'll explain what that means in a moment. Number one thing we're going to do, label our nodes, or identify the nodes. Then I'm going to label them. So I'm going to call this the ground reference, because that'll make this one at 60 volts. Call this V1, call this V2, call this V3. Okay, so everything is simple so far. Next thing I'm going to do, I'm going to define this, we call this voltage V sigma. That's the voltage across this. You can call that, say, V sigma equals 150 I sigma, which also equals V2 minus V3. And that's going to come in handy later. We can also quickly come up with an expression for I sigma. Notice starts at 0, ends over here. So 0 minus V1 over 100. So I sigma is V1 over 100. Okay, now we're going to get to the nodal part. These equations we're just going to need later, so I'm going to hold on to these. So I'm going to do a KCL at this node V1. KCL V1 is V1 minus 160 over 10 plus V1 minus 0 over 100 plus V1 minus V2 over 30, all equals 0. Now, one limitation, the supernode thing. We're going to try and start to do this for a node at V1 or V2 and V3. The problem is that nodal analysis can't handle voltage sources that aren't referenced to ground or some other reference node. So how do we get around that? we construct what's called a supernode. We basically will make this big node, which we pretend that this source doesn't exist, even though it does in actuality. We're going to come back and find that later to find the difference between V2 and V3. So let's say that is our super. So supernode, we're going to do KCL over there. So for that, we only have two currents leaving. First thing I'm going to consider is V2 minus V1 over 30 plus V3 minus 0, which is ground, over 20 equals 0. Now, how does that make anything easier? Well, it comes back to the equations that we derived earlier. We can figure out an expression for V3 in terms of V1 and V2 with a little bit of algebra. So I'm going to take this supernode equation and I'm going to simplify it. Well, let me write down, I'll call this equation 1, this is equation 2. So I'm going to take equation 2 and multiply everything in it by 30. So we're going to get V2 minus V1 plus 1.5 V3 equals 0. Now, we're going to notice we have V2 and V3. So if we can find a way to put V2 and V3 together, then we'll be able to include our 150i sigma, and then by extension this. So I'm going to move on to subtract. I'm going to subtract 2.5 V3 from both sides, and then add V1 to the other side. So we can get V2 minus V3, and then V1 plus, I said subtract, not add, 2.5 V3. Let me scratch that out. Alright. So now that we have that expression, we can plug in 150 I sigma over here. But remember, we already calculated I sigma. So 150 times I sigma is going to be V1 over 100. So negative 1.5 V1 equals the I sigma, or the equals V2 minus V3. So I'm going to plug that in over there. 1.5 V1 equals V1 minus 2.5 V3. We're going to pull the V1 to the other side. So negative 2.5 V1. Then divide by the negative 2.5 on the other side. And you'll notice this implies V1 equals V3. How is that possible? Well, this source is making that possible. So we're going to remember this and continue the analysis. So using that, we can plug that value back in and say, let's go back to equation 2. So let's bring back equation 2. And we have we'll just pull this down again, because we already did the expression. We'll do V2 minus V1 plus 1.5 V3 equals 0. But we know that V3 equals V1, because we did that little math thing. So V3 is going to be minus V1 plus 1.5 V1, which means that V2 minus 0.5, or plus, not minus, plus V1 equals 0, which means that V2 equals negative 1/2 of V1. Okay, so now we have all the, let me actually circle this real quickly. Now we have all the information we need to solve the rest of this. Well, not all the information, but we have an expression for V2 in terms of V1. So we're going to move forward with our first equation. So let me scroll down a little bit. Let me make sure I did that equation right. Okay. So let's bring back equation 1. We're going to multiply everything by 300. Why 300? Well, we have 100 here. So if we multiply everything by 100, we're going to have 100 over 30, which is not a pretty number. You can use that 3.333, but just to make it cleaner, I'm going to multiply everything by 3 again. So multiply everything by 300. All right, so that's going to make 300 over 10, so 30 V1 minus 30 times 160, so 4,800, plus 3 V1, which is 300 over 100, and then plus 10 V1 minus 10 V2, all equals 0. Then we're going to plug in this for V2. So what is negative 1/2 of V1? Or if V2 is negative 1/2 of V1, it's going to turn this into a plus. And we're going to divide this by 2. You end up with 5 V1. So now we have one equation and one unknown. Add all these up, so 30 plus 3 plus 10 plus 5 is 48. Move the 48 element to the other side. Divided by 48, V1 equals 100 volts. So now we can find out what V2 is. So V2 equals negative 1/2 of V1, which means if we take 1/2 times 100 equals negative 50. We also know from a previous expression that V1 equals V3. V1 equals V3. So if V1 equals V3, that means that V3 is also 100 volts. So now we can find out this current I and this voltage V sigma, and use that to find the power that's delivered by that dependent source. So to find V sigma, we're going to do V2 minus V3. So V2 minus V3 is negative 50 minus 100, which is negative 150 volts. And then I is just going to be V1 minus V2 over 30. So that's 100 volts minus 50 volts, so it will become 150 over 30. So 150 over 30 is 5 amps, which means that the power, let's say power sigma is going to be I times V sigma, so negative 150 times 5 equals 750 watts being supplied. And we have solved the problem using just a little bit of clever analysis using the super mesh technique. Not too bad. Okay, for 4.23, we're going to also use nodal analysis to solve a circuit, and we're going to find out the value of the 3 different branch currents, I1, I2, and I3. So the first thing I'm going to do, like always, is label the nodes. Well, mark them, identify the nodes, then label them. So these are all interconnected. And I choose this as my ground reference, which is going to make this minus 30 volts and this 80 volts right away. So we only have 1 voltage to solve for in the circuit. And then I can also mark down some currents. Now I'm going to just assume this direction. I'll just say that this is, let's call it I4. Call this current I5. And the reason why I'm marking those down is because we're going to need to know that the power dissipated equals power developed in the circuit. And to do that, we're going to need to know the current to these resistors, or at least the voltage drop across them. Anyway, so now that all the setup is out of the way, let's get to the solving. So we're going to, let me draw my arrows. These are going to be my nodal currents. Not necessarily the same direction as the actual currents. So I'm going to do a KCL at V1. And we're going to say that first one is V1 minus 30 volts. So that's going to become plus 30 volts over 5,000. You can leave it as 5,000 or 5K. Either way it'll work. Just make sure you remember that this is actually 5,000. And then V1 minus 0 over half a K, so 500. Then V1 minus 80 over 1K plus 10 milliamps leaving, all equals 0. So we have one equation, one unknown. Just going to do some algebra to find it. Multiply everything by 5,000. So I get V1 plus 30. Then we can actually just multiply everything by 5 because this is half a K. But if we left it as like, if this was 5,000, this would be 500, 1,000. Then we multiply by 5,000. But since we did the K's, we can just multiply by 5. So 5 divided by 1/2 is 10 V1 plus 5 V1 times, or minus 80 times 5, so that's 400. And then 10 milliamps, so 10 milli times 5K, that's 50 milliamps. Or not 50 milliamps, sorry. That'd be 50 volts, because we're turning everything into volts. All equals 0. Now, we're going to add up our V1s and everything. So we get 1, 10, 5, so 16. And then it's the 30, obviously. 30 plus 50 is 80. 80 minus 400 is 320. So move the negative 320 to the other side. 320 divided by 16 is going to equal V1. So V1 is 32 divided by 16 is 20 volts. So now we found everything that we need to solve to find the rest of the currents in the circuit. Everything now is just plug and chug. So I'm also going to find out the value. Let's do them one by one. So I1 is going to be V1 minus 30, so plus 30 over 5K. So it's going to be Did I do that? Oh, sorry. I did the wrong direction. Good thing I checked. So it's minus 30 minus V1, which is 20 volts. So minus 50 over 5K, I believe it's minus 10 milliamps. I2 is going to be V1 over 1K or 500. So I think that's 30. Let me check that real quick. 20 divided by 500 is 40 milliamps. Now we're going to do I3. And where is I3? Okay. I3 we're going to have to calculate using KCL. So if we consider the 80 volt node right here, we do KCL right there, we have nothing coming in. Oh, I'm sorry, we have 10 milliamps coming in. Then we have I3, I4, and I5 all leaving. So we'll do 10. I'll just write the numbers for now and I'll remember the milliamps later. So 10 milliamps coming in. I3 is unknown. We can calculate I4. I4 is going to be 80 minus V1, so 20, divided by 1K. So I believe that's 60 milliamps. Double check real quickly. 60 divided by 1,000. Yeah, it's going to be 60 milliamps. And then I5, same process. 80 divided by 4K. So 80 divided by 4K, I think it's 20. Yeah, 20 milliamps. Okay. So we know 60 milliamps and 20 milliamps. So that means that I3 equals negative 70 milliamps. Okay, so now we've found I2, I1, and I3. And we also have I4 and I5, so we can calculate the power developed in the circuit. So I'm going to scroll down just a little bit, and that should be fine. Okay, so the other thing we're going to need to know to solve for the power, we need to know the voltage difference across this source. So I can say that is, let's call that V2. And V2 is going to be 80 minus 20, which is our V1, so 60 volts. And using that, we can calculate the power supplied by that current source. So 10 milliamps, the 60 volt compliance voltage is going to be 600 milliamps, I think, or 600 watts, so 0.6 watts. And we're going to do the power supplied by the 30 volt source, so power supply 2. We have minus 30 volts from, because we have our current I1 going that way. So minus 30 volts times I1, which is 10 milliamps. So that's 0.3 watts being supplied. And power supply 3 is going to be the 80 volt source. There's 80 volts times minus 70 milliamps. So 80 times 70 to the 10 times 23, it's 5.6 watts. So the total power supplied is going to be 0.9 plus 5.6. So 6.5 watts if we did everything correctly. So let's go ahead and find the power dissipated. Go one by one. So call P1, that'll be the 5K resistor. So the current through the 5K resistor is 10 milliamps. It's going to be squared, so we don't care about the minus, times 5,000. So 10 milliamps squared times 5K. That's half a watt being dissipated. P2, we do the 500 ohms. So 40 milliamps squared times 500 ohms. And double check that calculation. Yeah, forgot the square. Times 500 equals 0.8 watts. Power 3 is going to be, let's take the 4K resistor. Doesn't matter which one. So that's going to be I5, which is 20 milliamps squared times 4K. So 20 minus 3 squared times 4,000 is 1.6 watts. And finally, the last resistor is I4 squared. I4 is 60 milliamps times 1 kilo ohm. So 60 minus 3 squared times 1,000 is 3.6 watts. So let's go add them all up. Power dissipated, 0.5 plus 0.8 plus 1.6 plus 3.6 equals 6.5 watts. So our answers make physical sense. There's no more energy coming in or leaving than there was to begin with. And everything's worked out. We'll go on to the next one. Okay, this may be the first time that you have seen mesh analysis. Typically it's something you learn about in physics 2, but if you're like me, whenever you take this course, I forgot about it basically, and I didn't remember very much of it. But it's just like any other circuit analysis technique. I'm not as comfortable in this one in particular, but I will do my best to help you guys out. So basically it all stems from, you have these virtual mesh currents, and you would call them something, usually I1, I2, something like that. And it doesn't matter if you make them clockwise or counterclockwise, just as long as you remain consistent in your math. You could even have one of them go the opposite direction if you wanted to. It would just make it a little bit harder to keep track. So anyway, it all centers on Kirchhoff's voltage law and these little currents. We consider a closed loop with this one current inside of it and compare them between the two. So anyway, I'll do K of VL for I1. I'm going to start over here and we make a complete closed loop. So I'm going to move counterclockwise, or sorry, clockwise. So we're going minus 80, gain of 80 volts, plus I1 times 75, which is the just Ohm's law, because we're doing a voltage, and remember V equals I times R, plus I1, and we also have minus I2 because our mesh current I2 is in conflict with our mesh current I1. So I1 minus I2 times 200, and then plus 125 I1. All right, so we can consolidate that equation. Let's say we have, I forgot to write equals 0. All of this equals 0. Let me just put equals 0. So I'm going to move the 80 to the other side. 80 equals I1. Let me put the coefficient in front. So 200 I1 plus 75 I1 plus 125 I1. So that is 400 I1 plus or minus 200 I2 equals 80. So I'm going to call that equation 1. We're also going to do another KVL for the second mesh current. I'm going to start here again. It doesn't matter where you start. It's all about just making that complete path. So we have I2, or once again, I1 minus I2, or actually no, this is going to be the other direction. So I2 minus I1 times 200. I'll actually move that down because I'm pretty sure this is going to be too long. Okay. 200, and then there's I2 times 150, so 150 I2, and we have a drop because we're going from plus to minus here. So 140 volts dropped, and then 250 I2 as the last one, and our loop is complete. So now it's going to simplify this equation. So I2, I1, I'm going to say that we have negative 200 I1, and then 200 I2 plus 150 I2, so plus 600 I2. Let me double check that. 200 plus 150 plus 250, 15 plus 25 is 40, yeah. And I'm going to do minus 140. Call that equation 2. Okay, so now we can find out what we can use any way that you want to do to solve a linear equation to figure out these values for I1 and I2 are mesh currents. So I'm going to use my calculator once again, so I'm most comfortable doing it this way. But you can do substitution, elimination, etc., etc. It's all up to you. There's 80. So minus 200x plus 600y goes minus 140. You end up with I1 equals 0.1 amps and I2 equals minus 0.2 amps. So the mesh current I2 is actually, in reality, would be flowing not clockwise, counterclockwise. That's just what the minus means. That's all it is. So anyway, if we know the current flowing through this resistor, then we'll know the voltage drop across it. So let's go ahead and find that out. So V equals I times R. So it's going to be, let me label these nodes again. So let me say that this is V1, V2, V3, V4, call this ground, call this 80. And we know, based on the way we wrote these equations, V2 minus V3 must equal 140 volts. So anyway, let's go ahead and do V equals I times R. So 80 volts minus V1 equals I1 times 75. So we can find V1 is going to be 80 minus 0.1 times 75. That's going to be V1, and let's punch this in. So it's 7.5, 73.5. Let me double check that. 80 minus 7.5, 72.5. So 72.5 volts as that voltage there. And then we can do the same process to find V2 because we know V1 now. So let's consider the 150 ohm resistor. I2 is going to be V1 minus V2, so 72.5 volts minus V2 equals negative 0.2, which is I2 times 150. So V2 is going to be 72.5 minus, well, it's going to be plus actually because minus. So 0.2 times 150, so negative 30, and then subtract negative 30 from both sides, you're going to get plus. So V2 is going to be 30 plus 72.5, or 102.5 volts. And we can find V3 using the equation we wrote over here. So V3 is going to be V2 minus 140, which is negative 37.5 with reference to the ground. And then we can find V4 using I2. So I2, let me do this real quickly. So 250, so V3 is minus 37.5 volts minus V4 equals I2, which is minus 0.2 times 250. And I think you know the drill. I'm going to do that. And then plus 0.2 times 250. V4 ends up being 12.5 volts. So now we have all the information we need to find these currents. There's other ways you can do it, but I'm going to find IA, IB, IC with these. So anyway, IA is going to be 80 minus V1, so 80 minus V1. V1 is 72.5 divided by 75, which if math works out, it should be 100 milliamps. 5 divided by 75. Yeah, so 0.1 amps. And as you'll notice, that is the same value as our mesh current. So we don't really have to do that if we don't want to. Anyway, IB is going to be, you could say IB is IA plus IC. So if we go back and skip to IC, you notice that IC is going opposite of I2, and by the same logic that IA is I1, we can say that IC is negative I2. So negative I2 would end up being 0.2 amps. So IB is IA plus IC. So 0.2 plus 0.1 is 0.3. Now we're going to do that same process for the second case where 140 is flipped around. So I'll be right back. Alright, so the second case we're going to do that same process, but the only difference here is we have this flipped around. And it won't really change very much, as you'll see. Alright, so let's draw these two mesh currents. I'll once again call them I1 and I2. They're distinct from the original mesh currents that we drew up. I'm also going to label the nodes. Although it's not necessary. I'll show you two different ways to solve this. The longer way that gives you more information, so to speak, which is the one I just showed here, and then the little bit of a shortcut, which we can do based off of our mesh currents. So anyway, first thing I'm going to do is a KVL for I1, and we're going to start right here. Doesn't matter where I start, but I'm going to start here. Actually, I'm going to start up here just to show you that it doesn't matter. So I'm going to start with I1 times 75 plus I1 minus I2, because there, once again, this current is conflicting with this mesh current, times 200 plus I1 times 125, and then minus 80 volts, because we're getting a gain from there, going minus to plus to return to our starting depth. Okay, so simplify this expression. I'm actually just going to copy the one I did up here because it's the same numbers. So 400 I1 minus 200 I2 equals 80. KVL for I2. This one's what's going to change. Another thing that's going to change is that this becomes a plus instead of a minus. So I'm going to start here. Completely arbitrary. I'm just going to pick that. So minus 140 volts plus I2 times 250. Well, yeah, we could write that. Then plus I2 minus I1, because once again the mesh currents are conflicting at that junction, times 200, plus I2 times 150, all equals 0. So you simplify that, you're going to end up with minus 200 I1 plus 600 I2 equals positive 140. So we scroll up, we can see that this second equation 2 is pretty much exactly the same as this one. The only difference is instead of minus here, it's plus. That's because we flipped the voltage source around. Anyway, so use whatever your favorite way to solve linear equations is. I did this in my calculator. So I1 equals 0.38 amps and I2 equals 0.36 amps. So based on that information, we can notice that IA equals I1 here, our mesh current. And we can prove that, we can prove that by using the same techniques we did up here, by solving for all the voltages and then using Ohm's law. Or we can just use that knowledge that we learned from the practice and say I1 equals IA. So I1 equals IA, which means that IA equals 0.38 amps. IB is once again IA plus IC. So we'll come back to that in a second. And IC is negative I2 because our mesh current I2 is going this direction, IC is going this direction. So that means that IC is 0.36 or negative 0.36 amps. So 0.38 minus 0.36 equals 0.02 amps. And there we go. We found all of the currents. And if you notice that they all use the same logic for finding these answers, you just gotta apply it differently whenever you have it flipped. Okay, so we're going to use mesh analysis once again to solve this circuit. Now, the one good thing that's good about with mesh analysis is you don't necessarily need a ground reference to get voltages in the circuit to make any physical sense, but I'm gonna label these nodes anyway. And I'll just call this ground, just in case it comes useful later. So 10 volts, E1, and this will be 4I sigma, or 4I delta. And then 4 volts. And this one we can calculate pretty easily, so but I'm not going to worry about that unless we need it, which we won't. So anyway, we're going to use mesh analysis to find the power delivered by the 2-ohm source. So I delta, IA. IA is in this closed loop, and you'll notice that this closed loop is just basically a voltage divider. So we can do a KVL here, but to find I delta is just Ohm's law. So the R equivalent is going to be 5 plus 3 equals 8. So I delta is going to be, maybe make sure that's a delta. I delta is going to be, it equals a little I delta. I did a big I delta instead of little in the mesh current, but they are the same current for the same reason we saw in the last problem. So anyway, V equals I times R. So we have 4 volts divided by 8 ohms, or half an amp, 500 milliamps. So right away, that's going to tell us the voltage right here. So 4 times I delta is 2 volts. So up here equals 2 volts. Alright, so now we're going to start doing KVLs. So I'll do a KVL for I1 first. So we have minus 10. I'm going to start from the bottom corner. Minus 10 plus 2I2 plus I2 plus, oops, sorry. Alright, I2, I did. I1. And then I1 and I2 are actually working together here. You'll notice the mesh currents flowing in the same direction. So we do plus plus times 16, and that makes a closed loop, so that equals 0. Can simplify that expression. We can say that 18I1 plus 16I2 equals 10. Do KVL for I2. I'm going to start from this bottom right corner. Doesn't matter where you start, but I prefer to start from the lowest potential. Anyway, so minus 2 volts, so 2 volts increase, and then there's I2, or 12 I2 voltage drop, and then once again I1 and I2 are working together here. There's 16, and then the loop is closed by at the bottom node. So let's go ahead and simplify this expression. There's 16I1 plus 16 plus 12 is 28 I2. And then negative 2, move it over to the other side, equals 2. So we have 2 equations, 2 unknowns. Oops. Once again, use any linear equation solving technique you like. I'm going to use my calculator. 18 plus 16, 10, 16, 28, 2. Okay. So my calculator is giving I1 equals 1 volt, or not 1 volt, 1 amp, and I2 equals negative 1/2 of an amp. Alright, so to find VO in the circuit, we need to find the current through that resistor. So I'm going to call that, let's say, I'll call that IO. So IO is going to be the mesh current I1 plus I2. So that's 1 minus 1/2 equals 1/2. And V equals I times R, so V equals IO times R, which is 1/2 times 16, 8 volts. So that means that V1 or VO equals 8 volts. So we've solved the first part of the problem. Now we got to find the power delivered by the current or the dependent source. Basically, all we have to do is P equals IV. So if, let me write down that, I'll just say that this current, this is, I'll call it I1. It's also the mesh current. So P is going to equal I times V, and we have negative 0.5 amps, and then there's 2 volts, so 1 watt is being supplied by that source, that dependent source. And there you go. Super simple. For 4.47, we're going to use mesh analysis to determine which ones of these 3 voltage and current sources is sourcing or sinking current. That is to say, whether it's generating or dissipating power, basically. And then we're going to find out the total power dissipated in the circuit. So to do that, we're going to need to know these voltages. So let's say that this is, I need to know the voltage across here. We need to know the current IA. We also need to know the current flowing through this resistor, or not resistor, sorry, this source, and we need to know VB. So to do that, we're just going to start out by drawing some mesh currents. I'm going to make them clockwise, but you can do them either direction, it doesn't matter. I'll call this I1, I2, and I3. Now, you can say that there's no other branches here, so the current flowing through this resistor, the 2 ohm one, is going to be proportional to, it's just going to be Ohm's law. So V sigma is going to equal I1 times 2. We do a better 2 than that. You can also do the same thing for this resistor over here. I'm going to say that, I'll just write that I delta equals I2. And then I'll leave the little arrow in. There's no harm in it. And then we want to find an expression for VB, because we're going to need that later on. So we can say that, well, actually, let me do these little labeled currents that are also in the circuit first, because these are from the problem statement. So you can say that IA is going to be I1 minus I2, or I'm sorry, I2 minus I1. And we know this because I1 is going this direction, I2 is going this direction, so they're basically kind of like fighting each other. Anyway, IB, I'm going to do the same thing. I2 is going this way, I3 is going up, so that means that IB is I2 minus I3. And using that, we can say that VB is going to be IB times R, so 20. Okay, so now we got a little bit of setup out of the way. Let's go ahead and look at the sources. So 9I sigma, or I delta, 9I delta we determined to be I2. So that's just going to be 9I2. as that's going to be the voltage across that component. So I can say that if I call that V1, this would be V1. So you can do that another time with the other source. The other source is 1.7 V delta. We have an expression for V delta up here. So V delta, or 1.7 V delta, is going to equal 1.7 times I2 times 2. So V delta, that means that this little current is going opposite of the mesh current I3. So I3, and here's our, we can call this whatever, just I. So that means that minus I3 equals 1.7 times 2, so 3.4 I2, or we can say that I3 equals minus 3.4 I2. Oh, not I2, I'm sorry. It's I1. I should be more careful with my notation. Okay. So minus 3I1 equals that. So I'm gonna box this up because it's important. And this up right here. Or this up here. These are all important, but I just want to remember these. Okay, so now we can start doing the analysis. I'm going to do a KVL for the mesh current I1. I'm going to start here and end at that same point. So minus 50 volts plus the voltage drop across that resistor, which is I2 times 2. Then the voltage drop across this resistor, which is 4 times IA, so I2 minus I1. And that equal, oh, I'm sorry, got the dependent source too. Then 9 I delta has a decrease, but we know that 9 I delta is equal to I2. All that equals 0. Gonna do another KVL for I2. So I2 is minus 9 I2, because that's the 9 I delta source, or increase through there. Then a drop, that's 4 I2 minus I1. Is that right? Let me think. I2 minus I1. I2. Oh, I'm sorry. I made a mistake here. I2 minus I1. And then we're going to do plus I delta times 5. And I delta we know is I2, so 5 I2. And then 20. What is this? I2 minus I3. All equals 0. Well, if we plug in 3.4 I1 for I3, we can remove one of the unknowns. We don't have to bother solving for that via the mesh analysis technique. We can just plug it in. So let's see, 20 times minus 3.4 equals negative 68, because it's 0.8 times 2 times 3 times 10. So yeah, 68. And then I'm going to put that in here. So this will become minus is plus, so plus 68I1. Okay, so now we can start simplifying our equations. We'll say that this is equation 1, equation 2. Equation 1 is going to be minus 4I1 plus minus 4I1. Did I do the wrong? Yeah, I did. I'm so sorry. I keep making these silly mistakes. I1 is here, so that's going to be I1 times 2 that, and then I1 minus I2. So 6I1 minus, there's a minus 5 over here, plus 9. So plus 5I2 equals 50. And do the same thing over here. So 68 minus 4, that's 64I1 minus 9 plus 4 plus 5, so that's 0, and then 20I2, so plus 20I2, there's no constants over here, that's all equals 0. Okay, so now we have a set of equations. You can use substitution on the other machine. Anything you want to solve the linear equations, I'm going to do my calculator, so 6 times 5 times, or 6x times blah blah blah, 50, 64x plus 20y, 0. Okay, so get a value for I1 as minus 5 amps, and I2 equals 16 amps. And by extension, we can find I3, because I3 is minus 3.4 times I1, so 3.4 times minus, so that means I3 is 17 amps. Okay, so now we have all our mesh currents solved. We can find out the rest of the stuff we need for the circuit. So the power, let's do the 50 ohm or 50 volt source first. The 50 volt source, we have current going, we have 5 amps going this way, and 50 volts is going plus to minus. Okay, so we're going to have a drop that's proportional to 50 volts times the 5 amps. So 250 watts being dissipated by the first independent source. That might seem strange to you, because typically they are sourcing current, but it just so happens that the voltage up here it's a lower potential, basically, so it's sinking current here. So we know that that one is definitely not supplying power. Let's try the other two sources. So let's do the second source. So I have a current IA here, and we know IA, we can calculate that. So it's going from minus to plus, so that's going to be a gain. Okay, so let's think about it. We're going to have PS2 going to be V, and V is 9 I sigma, or I delta, times I A. So that's going to be our expression we came up with earlier. IA is I2 minus I1, and I delta is 9I2, so minus 9 I2 times I1, or I2 minus I1, right? Yeah, I2 minus I1. I2 minus I1, so that's going to be, I'll just put it down below it, so negative 9 times I2 is 16, and then 16 minus 5 is plus 5, so 21. 21 times 9 times negative 16, end up with minus 24 watts being supplied. So we found out that one is definitely supplying power. Let's do the same thing for the dependent current source. All right, so someone's calling. Okay, anyway, so I3 is going that way. So it's going to be, let's see. There's a decrease. So we can find VB times I3. And VB is, what is VB? IB times 20. So let's do 20. And IB is I2 minus I3. So I2, oops, I2 minus I3 times I3. So that's minus 20, because this is 16 minus 17 times 17. So 2 times 17 is 34, times 10 is minus 340 watts. So these two are supplying power, and this one is dissipating power. So now we got to find the power dissipated by the rest of the circuit, which is just going to be I squared R for all these resistors. So let's do PD1, and let's start with the 2 ohm. So 2 ohms times I squared, so I1 squared times 2, so I1 is minus 5, 25, 50 watts. PD2, let's see. I'll pick the 5 ohm resistor. So I2 squared times 5. So I2 is 16 squared, 256. 256 times 5 is 1280. Let's do the 4 ohm one now. So that's going to be IA squared times R. So IA is I2 minus I1 squared times 4. So I2 minus I1 is 21. We just did it. Yeah. So 21 squared times 4, 1764 watts. And one more resistor. This one's going to be the 20 ohm one. So I'm going to do whatever IB is. I think IB is, yeah, I2 minus I3. So I2 minus I3 squared times 20. So that's 16 minus 17, -1 squared is +1, 20 watts. So I'm going to double check these answers, make sure that if you add them all up, equals, they equal each other. There's a power check basically. So we have the two sources, so 3024 plus 340 minus 1764 minus 250 minus 20 minus 50 minus 1280 all equals 0. So yeah, these answers make sense, and we've solved the circuit. Let's move on to the next one. For 4.53, task is to find all the branch currents. That's this one, this one, this one, this one. And then after we find all those branch currents, we're going to ensure that the answers are right by checking to make sure that we have the same amount of power dissipated as we do supplied. So to do that, we're going to use mesh analysis. So I'm going to start drawing little meshes, mesh currents I mean. And right away, you can say this one is 19 amps, because it's the only, there's a current source here, basically. I'm going to call this, I'll call this one I1, because I'll do that one first. I2 and I3. Doesn't matter what you name them. Anyway, so one thing we got to notice is there is a branch between these two essential meshes for the circuit analysis, and there's a current source in between them. So just like in nodal analysis, whenever you had, I believe I did earlier, a problem, it was a dependent source, but there was like a V2, V3. So like V sigma equals V2 minus V3. Same kind of deal here. Whenever you use a super node, you're going to have an expression for that mesh current, so to speak. So if you consider the directions of these mesh currents, we have I2 going that way, I3 going that way. 2IB equals I2 minus I3. Oh, is that right? I'm sorry. 2B, the arrow's going that way, arrow's going that way. So it's going to be I3 minus I2. Now what is IB though? Well, IB is going this direction, or is it right here? We have I1 is going this direction, and I2 is going this direction. So I can say IB, IB is I1 minus I2. So if you combine these, 2 times I1 minus I2 equals I3 minus I2. And using that, we'll just put everything on the same side, and you'll see why in a moment. So I'm just going to basically make another equation, because we're only going to have, when we combine these two meshes to make a super mesh, we're only going to get one equation from that, and there's only one other mesh in the circuit, so we need 3 equations for 3 unknowns. Anyway, so I'm going to call this one right here equation 1. Let me double check the work beforehand. Let's see, I3 minus I2. So I'll be adding 2 I2s to this side and subtracting 1 I1 to get 0. Okay, yeah. So now we can continue our mesh analysis. So I'm going to do KVL for mesh 1. I'll start here. So minus 4 ID. Oh, here's another thing. ID is going, there's no other branches here, so IG is going to, for the same reason that the 19 amps is that other current, ID is going to equal I3. So we're just going to throw in minus 4I3. And then we have I1 going this way, I2, 3 going that way. So we do scratch that out. 10 I1 minus I3 plus 5 times, see, I1 is going that direction, I2 is going opposite, so come on, going this direction minus that, and that all equals 0 because we closed that loop. Okay, now I'm going to simplify this expression. Just put it in sort of like a standard form. So 15 I1 and then minus 5 I2 minus 4 minus 10, so minus 14 I3 equals 0. We're going to call this equation 2. And I'm going to do a KVL for, I call this, here's my super mesh. It's going to include all this stuff. So KVL super mesh. I'm going to start at the same node. Doesn't matter where you start, but just for clarity, I'll start there. Okay, so we have 5 and I2 is going in the direction of our super mesh. Let me draw the super mesh current to be less ambiguous. Okay. So our super mesh current, we have I2 going that way, and I1 going that way. So I2 minus I1 plus I10, and it's I3 minus I1 minus 240 volts. We come back around, 40 times, let's see, I3, or sorry, I2 is going this direction. So it's I2 minus 19 amps equals 0. I'm going to simplify it. So let's see, we're going to have minus 15 I1, because it's minus 5, minus 10. And then 40 I2 plus 5 I2, 45 I2 plus 10 I3. Okay, now we got to do the constant. So we got 240 plus 19 times 40. 19 times 40, 760, so it's 1,000. Okay, so equals 1,000. So we have 3 equations for our 3 unknowns. You can use substitution, elimination, blah, blah, blah. Said it like 5 times now. I'm going to use my calculator. So I've been punching in as we go. And we're going to say that I1 equals 18 amps. I2 equals 26 amps. And I3 equals 10 amps. So using that information, we can figure out the branch currents. So it's just going to be pretty simple. We're going to compare our circuit diagram to our answers. So I'm going to start with I8. IA is I2 minus 19 amps. I2 is 26, so 26 minus 19 is 7 amps. IB, we have, let's see, IB is minus I2, or sorry, it's I1 minus I2, right? I1 minus I2, so that's 18 minus that, so negative 8 amps, and IC is going to be I1 minus I3. So 18 minus 10 is 8. And let's see if that makes sense real quick, because we have 2 IB coming into that node, and then say 2 by B, IC, and then IB leaving. So if we know IB is minus 8, and then 2 IB is going to be 2 times negative 8. So negative 16 plus 8 equals minus 8. So yeah, that makes sense. I see that. And ID is going to be IE plus IC. So, oh, actually, no, we don't have to calculate. ID, we know a priori is for an I3. ID is going to be I3. IG equals I3, which means it is 10 amps. And then finally, IE. This one is going to be I1, pretty sure. Let me double check it though. So we have ID going, or IE going in, ID and IC leaving. IC plus ID. And we know IC is 8. And then, oh, I'm sorry, let's see. Leaving, entering 10. Yeah, so it's 18. So it is I1. I didn't really have to do all that, but I did. Okay, so now we're gonna check our answers. I'm pretty sure they're right because we just checked them twice with 2 different KCLs, but never hurts. So let's go ahead and do it. I'm gonna have to actually probably I'm gonna move this down. The next problem, so I have enough space to do it. And let's start with the sources. So the first thing I need to do is I need to find the voltage across this source. So it's just going to be V equals I times R. So IA is 7 amps. And then 7 amps times 40. So 7 times 4 is 280. So you can say that this would be that. Okay. And then we're going to figure out power by that source. That's going to be 19 amps, 280 volts. So 19 times 280, 5320. And actually, we gotta check our currents though, because if we had a voltage 280 minus 280, this is plus. So yeah, that makes sense. We have it. This is absorbing power. It's sinking current. So I'll call that PS1, and we'll do PS2. That's just going to be we need to find the voltage across the current source. So I'll call that another V. And V, if we have minus 240 here, so minus 280, yeah, minus 280, okay, that makes sense. So minus 240, and then, so V2 would be Ohm's law, so V2V is going to be V equals I times R, so 5 times IB, 5 times IB plus, let's think, 40 IA. No, hold on. This one's a little bit tricky. Let's think about this a little bit. So if the voltage drop across 10 ohm resistor, so IC is 8 amps. So 80 volt drop across it. So if there's 80 volt drops across that, that means that, and IC is going that direction, so that means that V2 has to be 240, or minus 240 minus 80, so minus 320 equals V2. Sounds a little bit tricky. Okay, so it's going to be, power supply is going to be V2 times 2 IB, and we know IB is negative, so it's actually, let me think, because there's a minus over here, so the plus current is going minus, or plus to minus, so we're going to have minus in front. So minus negative 320 times 2 times negative 8. So 16 times 320, we have negative 5120 watts being supplied. And let's do PS3. PS3 is our 240 volt. This one's easy. So it's going to be, it's going from plus or minus to plus. So we're going to be delivering power. And there's minus 240 on one side and 0 on the other. Let's say there's, what is ID? Or it's 10 amps. Okay. So you don't have to really do any math. This is plus because we're going minus to plus. Yeah. So 2400 watts being supplied. So total power supplied is going to be 5120 plus 2400, 7250. So we got to make sure that everything else adds up to 50. So we already know PD1 is going to be PS1. So 53210. Let's go ahead and do the resistors now. There's only 3 resistors, so it won't take too long. So IB 64 times 5 is 320. So I'll say P D2 equals 320. PD3, I'm going to do 40 ohm resistor. So IA 7 squared times 40. 49 times 40 is 1960. And finally, the last resistor, PS4 or PD4. PD4 is 10 ohms. IC is 8. 64 times 10, 640 watts. So let's go add these all up. 75. I wrote the wrong answer, wrong number here. This is supposed to be 7520. 7520 minus 5320 minus 320 minus 1960 minus 640. Let me double check my math. Am I missing a source? Because I got a negative. Let's check the math. 10 ohms. I see 1960, 640. Did I forget to calculate something here? EI4 ID. Because we have 2400. I must be missing one source. Did I get all of them? Oh, the dependent source, of course, duh. I'm so silly. You guys are probably all yelling at me in the comments. Okay, so for ID, I have to punch that in. So it's probably going to be 720 if I got the rest of the answers right, because I get negative 720 for all these, and the currents are right for sure. So let's see, power supplied for, it's going to be for ID. And ID is 18. So 18 times 4, 18 times 4 times 10, right? Oh yeah, it's 4 times ID, and times the current. Yes, okay. ID was 10 amps, and we have how many amps? 18 amps flowing through it. So 400 times, or not 400, 40 times 18, 720. Yeah, so power check satisfied. And it's a really, really hairy problem. Just like the one with the super node, the super mesh, you just gotta be really careful. I'm not a big fan of mesh analysis for this reason. It's very messy, very quickly. Okay, so for problem 4.55, this one I think is the hardest one of this set. The task is to find out what value of IDC would make the 4 amp current source provide or deliver 0 power. So since we can't make this go down, then we have to make the voltage across it, say Vs, equal to 0, which means that V1 equals V2 over here, which also implies no current flows to this resistor, which will become important later. So I'm going to label these nodes real quickly. And at first they'll look like I'm going to do nodal analysis, but I will not. I'm loading these nodes for later, basically. I'm going to call this 0 volts. And the reason is because I figured out that was the lowest potential in the circuit, but you could pick any reference point. So if we call this V3, we call this V4, then V3 minus V4 is going to be 240. That's the equation for our voltage source. And now we're going to use mesh analysis. This might seem kind of counterintuitive, but this is truly the only way I was able to find it out what the answer was. Okay, so we're going to have these 3 mesh currents. Well, 4 mesh currents, but 3 unknown ones. And I call this I1, I2, I3, and here's 4 amps. All right. So let me just erase that real quickly, just to make more space to write. I gotta say, sorry, something funny happened. Say that KVL for I1, we're gonna start there. 20 I1 minus I2 plus 12 I1 plus 240 equals 0. So we can say that 32 I1 minus 20 I2 equals negative 240. We're going to do KVL once again for I2. I'm going to start at the bottom left corner. So 40 I2 plus 50 I3 minus I2 plus 15 I2 minus 4 plus 20 I2 minus I1 equals 0. Now, one interesting thing here. This is the voltage drop across the resistor. This is V1 minus V2. Now, we know it's 0, or we want it to be 0, so we can make Vs 0. So to do that, I2 must be 4. That means that the current through this resistor is 4 amps. And the current through this resistor, we'll find out later. But basically, using that relationship, we can find out what I1 is. So let's go back to our simplified I1. 32 I1 minus 20 times I2, which is 4, equals, plus 240 equals 0. Which means that if we do 240 minus 80, that's 160, minus 160 divided by 32. I'm sorry, the thing is happening again. My dog is acting up. Negative 160 over 32 equals minus 5 amps, which means that I1 is flowing opposite of the actual current in the circuit. So here's 5 amps going this way. Now if we do this, we have 4 amps going this way and 0 amps going this way. The only place where the amps could go is through that 20 ohm resistor. Now why is that important? Well, the voltage drop across the resistor is proportional to the current and through it and the resistance. So V1 minus V4 is going to equal 20 times 9. So 180 volts is the difference between V1 and V4. So if we can find V4, then we're in business. We'll know what V2 is, or what V1 is. Well, if you look at the other resistor, the 40 ohm resistor right here, the equation, so to speak, you could say V4 minus 0 divided by 40 ohms. Oh, I'm sorry, is 4 amps. Yeah. So, to find V4, we have 4 amps times 40 ohms, which is going to equal 160 volts. So, V1 plus 160 is going to equal, or sorry, let me do this again. 180 plus V4, which is 160, is going to give us V1. And by extension, V2. So let's see. 180 plus 160 is 340. So 340 volts. And V1 equals V2. So if we want to find the current through the 50 ohm resistor, which is equivalent to IDC, because there's nowhere else for IDC to go, V2 minus 0 is going to equal IDC times R, which is 50. So 340 volts divided by 50 ohms gives us IDC, which is, oh, I'm sorry, it gives us, not IDC. Let me label this real quickly. It gives us the current through this resistor. Call that ID. IDC would not be that. So ID. So that's going to be 6.8 amps. And now we're going to do one more KCL. We have 4 amps leaving and 6.8 amps leaving. And here is IDC. So IDC is going to equal ID plus 4, which means that IDC equals 10.8 amperes. I know it's kind of hard to follow along, it's crazy, and it doesn't really follow in line with the regular circuit analysis methods, but I tried doing this for like an hour and a half, and I could not figure it out until I started trying Ohm's law in different ways. So hopefully this helps you in some way when it comes to your future circuit solving assignments, etc., etc.